Okay, in this lecture, we're going to cover section 7.4, and this is on optimization. So this is going to be basically an application of all the ideas that we've learned in this section so far on um, finding relative or our local minimums and maximums through by computing the derivative. So basically, in this setup, you have some parameters or some quantities or some variables. There's some dependence of them. And one of the variables, which will be usually just your independent variable, your independent quantity or parameter, will be constrained. There'll be some constraints on it. It will only be allowed to take on certain values. And so this, for example, could be expressed by the fact that, or like, for example, it could be that you're dealing with fencing and you have a certain amount of fencing that you're allowed to use, and you want to say maximize the area. You want to maximize the area that you can create using this fencing. So the constraint will be the amount of fencing that's available to you, and what you're trying to optimize in this case is the area. So it's not, and it won't always just be maximizing. It could be minimizing, say. You want to minimize a certain quantity. Maybe minimize cost, say, for example. So there's a lot of different ways. There are a lot of different types of optimization problems, and we're going to look at a couple just to give you a feel for what these problems are like. So let me share my screen now. All right, so let's just jump right into work on some problems. So this one actually is the first example is basically the one I was mentioning about having you have the quantity of or you have a farmer is the problem says you actually let me just pull up the not the book but like extract the part of the problem that I want rather than just read it and you not being able to see what I'm reading. Okay, so we have here's this example here. All right, so let me see if I can do this. Okay, here we go. So we have this. The farmer has this is section 4.7, just to remind you. So it says a farmer has a certain amount of feet of fencing and wants to fence off a rectangular field which borders a straight river. And the farmer needs to and so there'll be no fencing along the river. And so what are the dimensions of the field has the largest area? So we have basically these certain quantities, and they're related to each other, and one of the quantities is constrained. So let me extract another picture from the book. So here's figure 2 from the book. Oops, let's see. Move that around. So here's the setup basically. So rather than me trying to draw it, I'll just get the picture for you. So what we have are basically um, the side lengths x and y. So we have a rectangle, which could be a square. X could be equal to y. We don't know. That's the point. We don't know what these parameters have to be. We're going to find out what they have to be. And so we have a couple constraints. So first of all, let's write down what these constraints are. So first of all, what we want is to maximize the area. That's the problem, right? We want to find the largest area. What are the dimensions? What are going to be the x and y that ensure that we have the largest area? Well, we have a dependence upon them. So we have a is equal to x times y. Now, at first, and this is so we want to, let me say we want to maximize the area. So this is going to be the area, of course. And at first, this is not so good because we have these two variables. And of course, I mean, when you go to multivariable calculus, you can deal with multivariable functions like this and talk about derivatives and finding local maximums and minimums of surfaces instead of curves. But we don't have the tools to do that. But thankfully, we have a constraint. So this is what we want to find, and we want to maximize this. But we also have a constraint. That is that the amount of fencing we have is limited, right? So we know that the perimeter can be only 2400, right? That's all we have. So however we choose X and Y, to form this rectangle, we can only do in such a way that we use 2400 feet of fencing. So what we know is that 2x plus y is equal to 2400. And this is good because this constraint allows us to eliminate one of the variables in the formula for A. So now we're just dealing with a single variable problem. So this implies that y is going to be equal to 2400 minus 2x. And since we're talking about and then of course this implies we can write the area as a single variable function. So a of x is to be x times y. We just solved for y. It's supposed to be x times 2400 minus 2x. And then of course that's going to be 2400x. It's x squared. And the only way for this to make sense is if x is between 0 and 1200. If x is, first of all, x is a side length, right? So it wouldn't make sense to talk about x being negative. So that's why we have this constraint. But then we also have this constraint here because if x were bigger than 1200, then y would be negative, and it wouldn't make sense um, to talk about y being negative either. So this is like forced upon. This is like we could say this is an additional constraint right here, forced upon by the situation that we're investigating. So now it went from having the area being a multivariable function to a single variable function. So now we can take derivatives. We can talk about derivatives. This is certainly differentiable, this function, and we can determine minimums and maximums. So let's take this derivative. So if we take the derivative of the area, that's going to be 2400 minus 2x. And what we need to find, remember, we're talking about the area as a function from this interval to the real numbers, from 0 to 1200. And so to find where the function is a maximum, we need to first of all find the critical points of the function. This is where local maximums or minimums could be. And then we need to compare those to the endpoints of the interval, right? I don't remember which section was that, but that was one of the sections in this chapter where we looked at finding the maximum, a global maximum of a function on a closed interval. And that's exactly the setup we have in this problem. So if you set the derivative equal to 0, I think it's pretty clear then that x has to be equal to, what is it, 1200, I guess? Oh, wait, no, I did not do this derivative right. Oh, I'm sorry, I didn't do this derivative right. That's why. This doesn't make sense. I didn't distribute properly over here. Sorry. So this right here, I just wrote x squared over here. It should be 2x squared. So then this will be 4x right here. And then if you set this equal to 0 and solve for x, I think it's pretty clear that I'll just let you do the algebra, that x is going to be 600. So this is going to be a critical point of the function. So what we need to do now is test the function at these various numbers. So at the endpoints and then at the critical point, and then compare and see which is the largest, and that will give us the x value for which the area is the largest. That is the side length represented by x for which the area is the largest. So if you plug in 0, it's pretty clear that the whole function is just going to be 0. So that's definitely not going to give us a maximum. And if you plug in 600 to the original function, you get 720,000, 720,000. And then if you plug in 1200, you also get 0. So this is definitely going to be the maximum. So now we know the side length for x, for which you have a maximum area on this interval right here. And then we can solve for y. So what we know is that y is equal to 2400 minus 2x, but in this case, x is 600. And if you solve for that, if you do this calculation, you get 1200. So then that means if we go up here, this will be, y will be the area for the, sorry, the side lengths for which this area is a maximum is when x is equal to 600 and y is equal to 1200. So in fact, it's going to be a rectangle, a proper rectangle, not a squares, a square, in this case. And yeah, so that's that. Sorry, I don't know, I'm a little off today. All right, so let's look at problem 2. This is example 2. Actually, I'm going to just extract the text like I just did. Okay, so this is example 2. So we have a cylindrical can is made up to hold 1 liter of oil. We want to find the dimensions that will minimize the cost of the metal to manufacture the oil, or the can, sorry. So we want to figure out, so we have a constraint, this that the volume has to be 1 liter, and so we want to figure out, we want to use the least amount of material as possible, because there's going to have to be obviously be a direct correlation between cost and amount of material needed. So here's the setup. Let me draw another or let me extract another diagram rather than trying to draw it. So this is the setup here. Oops. So we have this can right here, cylindrical can, and what we know is that, so what we need to figure out the amount of material used. So we can break this can up into pieces like this, and then just factor in all the surface area. That's going to be, the surface area is going to give you the amount of material you need. So we have these the top and the bottom are these discs right here, and then the side can be kind of unraveled. So basically you have a rectangle. So then what we have is that the surface area, um, so maybe I should, yeah, so the surface area is maybe, I guess, not proportional exactly. How do I want to say this? So what we want to minimize is the surface area. Yeah, I mean, it's what I just said a moment ago. There's a direct correlation between amount of material you'll need and the cost. So if you can minimize the amount of material you need, you will minimize your cost. So what's the amount of material we need? Well, it's just the surface area of this can. So we're going to talk about surface area, and this is what we want to minimize. We'll call it A, and the surface area is going to be the sum of the area of these two discs. So that would just be, so it's pi r squared, but there's 2 of them, so it's going to be 2 pi r squared plus the surface area of this piece right here, which is just the area of it. So this will be 2 pi RH. I'm guessing they're just assuming that these like don't have, I mean, this is not entirely accurate, I guess. That's what's kind of tripping me up a little bit, because they're not taking into account the fact that these have depth also. They're not, there's there's no height to these. Well, there's no depth to it. Yeah. Anyways, um, this is not going smoothly as smoothly as I anticipated. Anyways, so we have the constraint. What's the constraint in this case? This constraint is that the volume has to be 1 liter. So, but I guess they're gonna put everything in cubic centimeters for whatever reason, I guess. So 1 liter is the same thing as 1,000 cubic centimeters. So what we know is that the volume has to be 1,000. What's the volume of this thing? Well, it's just another fact I'm gonna throw at you. If you don't worry about memorizing all these formulas. Well, one, this is an online course, so you can just look up the formula. Everything is open book basically. And two, most of the formulas I will give you, unless it's like the area of a rectangle, which everyone should know. So the volume of this thing, this can, is going to be pi r squared h is equal to 1,000. So this is like our constraint. So we have our surface area is expressed as a function of r and h, but that's no good. We don't want multivariable. But because of the setup of the situation, we have this constraint here, and we can actually eliminate the variable h. So this one, when you solve for h, you get 1,000 over pi r squared. So the surface area becomes a function of r, and it's just going to be 2 pi r squared plus 2 pi r times h, but h we just determined it was 1,000 over pi r squared. So now we want to minimize, so want to minimize a r, well yeah, this function a of r, sorry, for yeah, so we do want to minimize this function right here. So let's see. So now we need a derivative in this case. So the derivative is going to be 4 pi r. Maybe I should have simplified this a bit, actually. Probably should have just started this video over because this is really honestly terrible. So let me simplify r a bit. So it's going to be 2 pi r squared plus 2,000 over r. So now this is what we want to minimize. We want to minimize the surface area. So the derivative in this case is going to be 4 pi r minus 2,000 over r squared. And if you solve that one, then you can combine things a bit to get 4 times pi r cubed over minus 500 over r squared. So we need critical points to find the critical points now. So that is points where the function is the derivative is 0 or not defined. So no, it's not defined at r is equal to 0, but being equal to 0 doesn't physically make sense, right? So it's not the r being 0 is not in the domain of the function. So we can say r equals 0 not in domain of the function a of r. However, we can, if we set the function equal to 0, the derivative, you're gonna get the numerator is has to be 0. And that's gonna, when you solve for that, that's gonna imply that r is the same thing as the cube root of 500 divided by pi. So um, the only drawback here is so here's a drawback. So we have to be a bit careful here because we're not talking about a function on an interval. So a is a function from 0 to infinity to r. And this is, in fact, it's actually not even, it's not just r, but it's going to be all the positive numbers. So this is going to be right here, sorry, there's dogs barking that's distracting me. So the function is the positive numbers to the positive numbers. This is not a closed interval. So it's not like I can find the critical points and then test the value of the function on the endpoints of the interval and then on the at the critical points. So I can't do that. So I can't test the function at the endpoints of an interval and then at the critical points and then compare what I get and just see that, oh, this is a minimum because this is not a closed interval. So I have to actually do a little bit more careful analysis. But let's draw the function again. I mean let me write down the derivative again. So it's gonna be 4 pi r cubed minus 500 over r squared. And if you know that when r is going to be less than this critical point, whoops, then the derivative is negative. So that means a of r is decreasing on 0 to I guess this critical point right here. And so it's constantly decreasing. And but when r is bigger than, so let me say when r is bigger than this number, the derivative is going to be positive, so it implies that a of r is increasing on the interval from the critical point. Let me fix that. To infinity. So that just means that this implies that r equals this critical point just corresponds to the minimum. And in fact, it's going to be this corresponds to the I guess what we were using, the absolute minimum, our global minimum, absolute or global, oops, minimum. Because so the function is decreasing up to the critical point, and then suddenly increasing, it suddenly goes to increasing. And so that means that this point right here corresponds to a minimum, but the function just keeps increasing. It never goes back down. So it can't go below that point. So this just has to be the minimum point. So this right here, this point right here is going to correspond to minimal cost. What it's going to correspond to is minimal surface area and hence cost. Hence cost. It's going to give you the minimal surface area. Hence, since we know surface area is in correspondence with cost, this will give you the minimal cost. So let me pull this down a bit and just write a little bit more on this. Um, so if this is the radius that gives you that, then you can actually work out what the height is also, because the height is 1000 over pi r squared. And if you plug that in and simplify, you will get, um, well, let's just plug this in, I guess. Um, this doesn't make sense what they're doing in the book to me. Oh, I see. Okay, interesting. All right. So if you plug this number in, squared, yes, squared, and you do the simplification, you're going to get 2 times cube root of 500 over pi. But we just determined that this is our critical point, so it's going to be 2 times r actually. So to minimize the cost of the can, your radius should be this, and then your height should be twice equal to twice the radius, or which is the same thing as the diameter actually. So so and we're talking about this radius right here. So we have the radius, and the height we just determined has to be twice this radius of this disk, which is the same thing as just the diameter of that disk. So here's also, let me pull up the book. Here's a plot of the function. So you can see we have this minimum value right here. That corresponds to this right here. And the function is decreasing as you go from left to right to this point, and then suddenly increasing, and it never goes down. So not only is this the local minimum, but it's actually the global or absolute minimum for the function on the whole interval 0 to infinity. Oh, and this is actually just a summarization. Let me see this. So if you have, so here's the first derivative test for absolute extreme values, or absolute extrema. So you have C as a critical point of the continuous function defined on an interval, and this is not necessarily closed, which is the point of the last problem, not necessarily closed. So in that problem, we were talking about the interval 0 to infinity, and that's definitely not a closed interval. But even if that's the case, you can still get around this. You can say that if you know the derivative is positive for all values to the left of your critical point, and then so in other words, you're increasing to the left of C, and you're um, then decreasing to the right of C, and this happens on the entire interval, the whole interval, then you can say not only is f of c a local maximum, but it's actually also an absolute maximum or a global maximum. Just like on the flip side, if you are decreasing on the left of the critical point and then increasing on the right of the critical point, then f of c is not only a local minimum, but it's the global or the absolute minimum, just as in the case of the example we looked at. So I guess there's this alternative solution I didn't notice before. Um, okay, so you can use implicit differentiation to solve this, I guess. So you have this is our equation relating these parameters. You have this as our constraint. And instead of eliminating h, we're going to differentiate both of, oh, okay, that's interesting. You differentiate both of these implicitly. The minimum occurs at critical number only, so we set a equal to 0 and simplify. Oh, so it's just like solving an equation almost. That's interesting. I'll let you look through that, read through that on your own if you want. All right, let's do one more example. All right, so this example is number 3. So we want to, actually, let me just do what I've been doing. and extract the text. All right, so see, so we have this. The problem this is example 3. We want to find the point on this parabola right here that is closest to the point 1, 4. So let me also extract the diagram so you can see what's going on. So we have this is the setup right here. So what we want to do is, so we have just a generic point xy on the curve. And what we want to do is we want to minimize, oops, this is the distance d between um, the point on the curve x comma y to this point right here. So we want to minimize this distance right here. So want to minimize this, and our constraint is that we're not just talking about any old point x, y in the plane, but the point actually has to live on this curve. So the constraint in this case is this equation right here that relates the two. All right, so now here's like a fact. Um, we minimize d is minimized if and only if d squared is. So if we can minimize d squared, then we will have minimized d. And that's basically because this square root right here is an increasing function. It preserves the order. Um, so this is going to be useful because we want to eliminate the square root if possible. So let's write that down. So d squared. What we'll do is we'll just use a different name now. So first of all, d squared is going to be equal to x1 squared plus y minus 4 squared. And we know that x is equal to y squared over 2. So that implies if we substitute that in, we have a function f of y, which is going to be defined to be d squared, is going to be y squared over 2 minus 1 squared plus y minus 4 squared. And so what we want to do is we want to minimize this function. And if we can do that, we'll find the y coordinate that gives us the point on this parabola that is closest to this point. And once we know the y coordinate, we can use our constraint to find the x coordinate. So what we need to do is take a derivative. So if we differentiate this using just all our rules, we get 2 times 1/2 y squared minus 1 times the derivative of the inside function, so y squared over 2, which would just be y, plus 2 times y minus 4, and that's it. And then if you simplify this, I'm not going to go through all the steps, but if you simplify this, you're gonna get y cubed minus 8, and then what you can see then is that if you, well, let me just say it right here. So if you set this to equal to 0, then y has to be the same thing as 2. So now we're kind of in that same problem as we were in example 2. We're not talking about y, the value of y is not, the domain of y is not constrained to an interval. Y, if you look at the picture, this function goes off to infinity here and then negative infinity down here. So like every value of y on the x-axis or the y-axis, you can go far enough out and it will hit the curve. So there's no constraint on what y can be. It can be any real number. So we're not talking about y in a closed interval, but we can use that, we can look at the critical point and determine whether it's like increasing or decreasing to the left or to the left and or the right of this critical point. So this is our critical point. And and you'll notice that if y is less than 2, then f prime is negative. So this means that um, f is decreasing on the interval negative infinity to 2. And then if y is bigger than 2, then f prime of y is greater than 0. So this means it's increasing. It's increasing on 2 to infinity. So it's decreasing and then increasing. So this corresponds to, so y equals 0 corresponds to local minimum. But because this is the only critical point, and after once you're go past 2, it never goes back down. The function never goes back down. It's always constantly increasing. This actually has to be the global or absolute minimum. So it actually corresponds to global slash absolute minimum. So now so if this is the y value corresponding to our absolute minimum, then x, which is equal to y squared over 2, is going to be 4 over 2, which is 2. So the point on the curve is going to be 2 comma 2, I guess. So in summary, then what this whole all of this shows is um, that the point on the curve y squared is equal to 2x closest to 1 comma 4 is the point 2 comma 2. And this is really truly a point on this curve. It satisfies the equation. And according to the above work, it's actually going to be the closest point. All right, so there's a few more examples that I encourage you to read through, but this is all we're going to do for this section, in this section. So let me stop share.